Welcome back to our mini-series on measurement-based quantum computation. So this here, what you see, is the outline of this entire course, this entire mini-course, and we have now completed the overview and we move into the technical portions, and that begins with universality. And universality is the topic of this lecture and the next, and there's just one item on the menu, and that's the universality proof. So this is just to recap how we started out. What you see here is a two-dimensional cluster state, where certain qubits are measured in certain bases, and what this amounts to is creating long-range entanglement between distant positions A and B. This is one thing that you can do with cluster states. And so the question arises, how far can we take this? And well, we can take it to universal quantum computation, and this is what this mini-series is about. So in this part, we want to study the proof of computational universality. So let's look at our situation, and what we have here in front of us is the 2D cluster state. And every symbol that you see, all the arrows and all the dots, they represent cluster qubits being measured in certain bases. And different bases have different logical effects. And so we start out with those cluster qubits that are measured in the eigenbasis of sigma z. Essentially, they are just removed by being measured in this basis. And so we remove them, and what we are left with is this network. And indeed, this network represents a quantum circuit. Now, let's make that explicit. We make it explicit by tearing it apart. We identify various pieces on that network that correspond to gate action. So we find that some regions correspond to CNOT gates, other regions just represent wire, that is, information transmitted from one point in the cluster to another point, and then there's one qubit rotations, and together these gates make a universal set. Yeah. And then there's one final thing that we need to explain, and that has to do with a measurement. So when we perform a measurement, we get an outcome, and that outcome is random. So now we have two choices. We can retain it and use it for something, or we can discard it. Discarding wouldn't work, because then effectively we would trace over that qubit, and that wouldn't have the desired logical effect. So we will need the gained information, the measurement outcome, for something. But what is this something going to be? We need to figure that out. All right, so what we have done so far is dissecting the computational scheme. We were looking at the scheme as a whole and then decomposing it into its elements. Now we do the reverse process, we do the synthesis. That is, we start with the elementary parts, with the wire, with just the identity gate, and then with the gates from the universal set, and then we start composing them. So we build the computational scheme from its parts. This is how the universality proof will work. So what you see here are the first 3 steps, the first 3 of 6. And this is what we are going to do in this lecture. We will explain the simplest gate, the identity gate, in step 1. Then we will explain the 1 qubit rotations in step 2. And we'll talk about the CNOT gate in step 3. Okay, then there will be 3 more steps in the proof. Step 4 will have to clarify the rules of composition. So we are simulating unitary logical gates here by measurement, and so we need to make sure that the simulation of these gates in the measurement-based fashion, they compose in exactly the same way as the gates themselves compose. That is step 4. Then we have to talk about what we began with in the decomposition. We have to talk about the effect of removing the qubits that are measured in the Z basis, that is step 5, And then finally, we will talk about the effect of measurement outcomes. Okay, so let's begin with step 1. This is now the explanation of wire, the explanation of the identity gate. So let me begin what you see on the left of the slide. You see 3 qubits entangled in this cluster state fashion. So the bottom 2 qubits start out in an eigenstate of sigma x, as what we saw before. But then there is a qubit on top of them that is now in a general 1 qubit state. So that is psi. Yeah? And by measuring the top 2 qubit, we find that the state of the first qubit is now teleported to the third. This is what we now want to explain. And to provide this explanation, we have the 4 panels that you see here, and we go through them in order. So let's begin with panel number 1. So here the process of creation of the cluster state with input and the subsequent measurements are represented by a quantum circuit. So at the beginning you see the inputted quantum state psi and the 2 bystander qubits in the state plus and the eigenstate of sigma x with eigenvalue 1. Next, you see 2 entangling gates. These are conditional phase gates. They exactly represent the action of the Ising Hamiltonian, what we earlier described as unitary interaction with the Ising Hamiltonian is now described in the language of quantum gates. Yeah? And the conditional phase gates do exactly that. So that's the part in the middle of diagram number 1. And then on the right side of that diagram are the final X measurements. So that describes the creation of the cluster state with input and its subsequent measurement. This is the situation that we are going to explain. Now, this is precisely the procedure that's being performed in wire. And now we want to transform this by equivalence transformation into something that you already know. And that thing is teleportation. So we rewrite this wire as a teleportation protocol. And so we are now moving from panel 1 to panel 2. And well, there isn't much changing except that between the 2 conditional phase gates that represent the Ising interaction, we make the insertion of an identity. And the identity is inserted as a product of 2 Hadamards, which precisely give the identity. Okay. So this is what we do, and subsequently we will treat the left and the right Hadamard differently. Okay, so this was an equivalence transformation. Nothing has changed. And we now move to panel number 3 and do another equivalence transformation. And what we do is we take the final measurements and propagate them backwards in time. So we propagate them to act between the 2 Hadamards. So this means these measurements must be exchanged in their order with a conditional phase gate and with 1 Hadamard gate. And well, these measurements and these gates, they do not commute, so we cannot just exchange their order. That would not be an equivalence transformation. Instead, what is going to happen is that the observables transform when they are being propagated backwards. So they are acted on by conjugation. So this is an exercise that you can do by yourself. When you transform these measurements backwards in time, they are conjugated by the action of those gates. So let's do this in an example. So let's talk about the X measurement on the upper qubit. So let's propagate this backward in time. So the first thing is that it propagates to before the conditional phase gate. So what is going to happen is that the observable X on the first qubit is converted to X on that very first qubit times Pauli operator sigma z on the second qubit. Now we take this and propagate it before the second Hadamard gate. So the x on the top qubit is unchanged and the z on the second qubit is converted into an x. So the measurement that used to be x on the upper qubit becomes the measurement of the correlated observable x tensor x. So that's also something that you see in panel number 3. Now we do the same with the other measurement, the x measurement on qubit number 2, the middle qubit. So I spare you the analysis here. You can do this by yourself. And when you propagate this, what you find is that x on particle number 2, when propagated backwards in time, becomes a z tensor z. Now this is the second measurement we see. And you can explicitly verify that these measurements still commute as they did before, because they have to. And now let's look. So this completes panel number 3, and we are now basically identifying what we have in this picture, and this proceeds by moving to panel 4. So this is the last step to explain. So the measurements that we have here in the middle, together they form a Bell measurement, a measurement in the Bell basis. So that takes care of that, and after the measurement, what happens to these two qubits subsequently, we don't care about. And what remains to be identified now is the left lower part of the circuit. So the subcircuit acting on the two lower qubits, beginning with the conditional phase gate, followed by the Hadamard, and acting on these two qubits in the state plus. So this subcircuit is the creation of a Bell state. That's easy to verify. You may do this yourself. And so now what we have in this circuit, just rewritten what we had starting out with, is our quantum state to transmit, psi, supplemented with a Bell state, and then a Bell measurement acting on those qubits. This is precisely the teleportation circuit. So this completes the explanation of wire. So now comes step number 2. We are done with the wire. We want to do some real work. We want to achieve something. So let's talk about the 1 qubit rotations first. So we will continue with something similar that we started out with. So on the left panel, you see a situation like wire. We have 3 qubits, 2 qubits in the state plus, the input state, psi, entangled in the cluster state fashion. And then comes the tiny, tiny but important difference when you compare it to the wire, namely the measured observable are changed. Previously, we had observables x only. Now we have observables a and a prime, and we will fit in later what these are. But this is where the change is compared to the situation we saw before. Let's now move to the middle panel. Again, we are converting from one panel to the next by equivalence transformations. So nothing really changing, just the interpretation changes. So in the middle panel, we are reorganizing the order of operations, and we can do that always as long as the operations commute. So what we are exchanging in order here is the measurement of the first qubit and the conditional phase gate between the lower 2 qubits. These gates do commute because they simply act on different qubits. And then there's a final exchange of ordering, and that's the preparation of the third qubit. It also commutes with the measurement on the first. Okay, and when we now look at that circuit in the middle, we find that there is one and the same structure repeated twice. If you look at these red boxes, it's exactly the same thing repeated 2 times over. And next, we are going to study what these boxes do. Okay, So part A we have just done. We have decomposed these operations in two like parts. Now let's move to step B. And now we are fitting in a specific form of the observable. So we say that our observable A is the Pauli observable sigma x conjugated by some rotation uz about the z-axis. So this is the observables that we're looking at. If you work it out, that's some linear combination of sigma x and sigma y. Okay, these are our observables of interest now. So let's see what they do. So let's look at the sequence of 4 panels that are connected by equivalence transformations again. So let's first simplify the observables. So we have this sigma x conjugated by the rotation about the z-axis. This is our observable, and we can easily represent this in our circuit now as first a rotation about the z-axis and then measuring our old observable sigma x. That's the second panel. Now moving to the third, we make the observation that the rotation about the z-axis commutes with the conditional phase gates. So we can, instead of applying the rotation after the conditional phase gate, equivalently apply it before. And that's what you see in the third panel. So we now have the input state psi acted on by that rotation first, and then whatever the conditional phase gate and the x measurement do. Yeah, what do the x measurement and the conditional phase gate do? Well, that's something now for you to work out on pen and paper. This is a 2-qubit Hilbert space. You'll be able to do that yourself. I just give you the answer. So what this conditional phase gate and that measurement do is they give you a Hadamard gate preceded by a Pauli flip that happens or does not happen depending on what the measurement outcome is. So in total, so this half step, this half teleportation step now does the following sequence of gates. It does this unitary rotation uz that first appeared in the definition of the observable. Then it does this byproduct operator sigma z that happens or doesn't happen depending on what the measurement outcome is. And finally, we have the Hadamard. So this is what we get out of this half teleportation. And remember step 6. We already talked about it. I explained to you that the measurement outcomes will have an effect. And here you see for the first time what this effect is. It gets in this funny byproduct operator that we do not really want to have, but we get it anyway, and we will have to deal with it. Yeah, so dealing with it comes up in step 6. For now, note that it is going to be there, and there's nothing that can be done about it. So this completes that part of the rotation, but there's more to say. All right, so let me summarize what we've done so far. We have this rotation involving 3 qubits, 2 measurements in somewhat complicated bases, and we have subdivided them into 2 like parts, and we have understood what such a part does. Namely, it takes the input state, it rotates it by some unitary uz about a variable rotation angle, it does this byproduct that is dependent on the measurement outcome, and then it does a Hadamard. So this is what one half teleportation does. And now let's put the 2 half teleportations together. So this is what you see in this set of formulas here. So you have this block, Z rotation, byproduct, Hadamard repeated twice. And now we are reordering these operations. So what we do is the earlier Hadamard, we move it right to the end to act together with the other Hadamard to cancel. So what this does is it converts the second rotation, which used to be about the z-axis, into a rotation about the x-axis. This is by conjugation. So that's the first thing that happens. And also it conjugates the second byproduct, Z to the power S prime. It also conjugates this into a byproduct sigma X, dependent on the same measurement outcome. So these two things happen, the two Hadamards cancel, and so the effect now is that we have a Z rotation, an X rotation, and two byproducts, a Pauli Z and a Pauli X. So this is the outcome of this sequence. So let's summarize this. Altogether, what we find when we combine more such blocks is that we have alternating sequences of Z rotation, X rotation, Z rotation, X rotation. How many do we need to do a general SU2 unitary? Well, 3. That's the Euler decomposition. Okay, so this completes the explanation of the rotations. We have one gate remaining, and that's the C0 gate. You see on this slide two versions of it. I will not do it for you. This one you'll have to do by yourself. And my advice is to do the one on the right. That's the simpler one, the one that invokes only X measurements, no Y measurements. You can use all the tricks that you have learned up to this point. There's one additional hint that I give you. So this pair of neighboring X measurement, whether they occur horizontally or vertically, doesn't matter, they always implement Y. Maybe you find this information useful. Otherwise, you're on your own now. Try to prove the correctness of the C0 gate. So that completes the universal gate set. Let me summarize what we have done so far. We have done the elementary parts. We've done the wire piece, we have done the 1-qubit rotations, and in fact all SU2 rotations, and you have done, hopefully, or will do, the C0 gate. That completes the components. The remainder of this proof will be about composition, and that we are looking at next time.